In most cases, integral calculations are not actually required here, as the above formula reduces to a simplified version when applied to the most common loading scenarios as discussed next. The simplest and perhaps most common axial loading scenario involves a member subjected to one constant internal axial force N. This member has a constant cross-sectional area A and constant elastic modulus E, so it's by far the simplest possible scenario of axial loading. So we have an applied external axial force P, in this case showing tension. We have X measuring length along the bar or the member, L the total length of the member, and delta being some total axial displacement. And as we said, it has a constant unchanging cross-sectional area and constant elastic modulus. So here, the relative axial displacement formula reduces to the following simplified version. Okay, taking this formula here and noting that N, A, and E are constants, we have delta equals NL over AE. Another common scenario involves a member subjected to varying internal axial forces within different segments of the member. That is, that the normal force N varies abruptly segment to segment. This member is referred to as a segmented member. The cross-sectional area A and elastic modulus E could also vary abruptly segment to segment. Within each segment, N, A, and E are constant. So here is a scenario that was just described. We have this segmented bar. It has varying values of internal normal or axial force N, varying values of cross-sectional area A, and could have varying values of elastic modulus E. Okay, we have various points given to us with different loads being applied, axial loads, different lengths as well, L1, L2, L3, and L4. In this diagram, there are 4 distinct segments of member, noting that a new segment begins when there is a change in N, A, and or E. Thus, the relative axial displacement formula reduces to a discrete summation as stated above in this equation here, where delta equals summation NL over AE, meaning the summation of the NL over AE values for each segment. In this case, there would be 4 terms in the summation, one for each segment. There are exactly 4 segments. So starting on the left side, okay, we have our initial point here. That's going to start segment 1. Moving from left to right, once we encounter a new axial load, a different cross-sectional area, or different elastic modulus, a new segment begins. Okay, so we have segment 1. As soon as we encounter load P2, segment 2 begins. Then as soon as we encounter this change in diameter or change in cross-sectional area, a new segment, segment 3, begins. Then we encounter this new axial load here, and thus segment 4 begins till the very end. So we have 4 distinct segments, and therefore 4 terms in this summation. Lastly, let's mention the sign convention for axial loading scenarios. The sign convention used for axial loading scenarios is discussed next, and it's very important to keep this consistent and to use it properly. If an axial force causes tension and therefore elongation, then N and delta are both positive. If, on the other hand, it causes compression and therefore contraction, then N and delta are both negative. And those are being illustrated here. In this case, we have a tensile normal force that causes elongation, so N is positive, delta is positive. Here we have an axial force that causes compression, a compressive load, and therefore N is negative and delta is negative. When calculating relative axial displacements, if the resulting sign on delta is positive, then that segment elongates, meaning those 2 points, A and B, move away from each other. If the sign on delta is negative, then the segment contracts, meaning points A and B move closer to each other.